Hi everyone. Welcome to the seventh webinar of the Chemical Engineering Evolution. It is a great pleasure today to celebrate our centenary year with a theme of built environment and transport. We are here to highlight and celebrate the enormous contribution that chemical engineer has made to society over the last century. We will debate on built environment and transport, focusing on developing sustainable zero carbon solution for the future. The webinar will be about 90 minutes by presentation and discussion. And there is a chat box. The audience can write their question and their highlights there. Then I'll try my best to pass to the panel. The built environment is advanced a great human achievement and ongoing and increasingly difficult challenge as we juggle comfort and convenience with the impact on natural and social environments. As we become more sensitive and aware of impact, the role of a chemical engineer becomes more significant and visible. As human lives increasingly concentrated in towns and cities, we influence our surrounding in myriad ways, from air, lights, noise, water and visual pollution to municipal waste and wastewater. And also our life impacts the soil, waterways, and the coastal line. And our industrial waste sometimes results in major disasters. So in that context, safety and sustainability have now become a central ideas when creating built environment and transport networks. The challenge rests in how to achieve this while maintaining equitable access, reliability, and economic and environmental sustainability over a long time. Decarbonizing heavy vehicles are not quite as advanced, and with the weight and size of batteries limiting the potential of the electric trucks, chemical engineers continue to investigate alternative fuels, including their safe and economical manufacture. Electrical fuels use green hydrogen or CO2 to form a hydrocarbon with zero net greenhouse gas emissions. Although technology is still in its early phase of the development, e-fuel could make a significant contribution to zero carbon transport system, and also not just a heavy haulage, but in aviation, one of the most energy intense forms of the travel. A carbon neutral maritime industry is similarly reliant on the alternative fuels such as hydrogen, ammonia, or liquid organic hydrogen carriers. Chemical engineers are developing safe and efficient methods to manufacture and handle these fuels. Another chemical engineer innovation is the hydrogen fuel cell, which has potential in trains for both long distance and local. Successfully decarbonizing our transport networks and buildings will rely on further innovation of chemical engineers, coupled with a policy to provide incentives for upscaling and implementation of these technologies. This webinar panel will discuss on how chemical engineer of future will contribute to addressing the major challenges for the livable future, modern or smart cities and built environment. And also we are going to discuss how chemical engineer of future will contribute towards the decarbonization of the transport sector. Here, I'm delighted to introduce our distinguished panelists. First is, I think I would like to invite, all the camera is on, right? Claire Miller. She is the Director of Technology and Innovation of Octopus Electric Vehicle, part of the Octopus Energy Group. Claire is passionate about solving real-world problems, delivering new technologies to market, and most importantly, into the hands of users to make a positive impact on the world around us. She works at the cutting edge of EV adaptation, energy technology, and the smart connected grids, including the Power Loop Vehicle to Grid V2G project, which she led from January 2019. Keller has a master in mechanical engineering from Imperial College London, and in 2022 she been recognized as one of the 30 leaders more likely to usher the automotive industry to its electrified future by Business Insider, and a top woman in EV in technology by the EV Summit. Next, I'm going to introduce and welcome Titi Olidi. She is Senior Process Safety Engineer, Supercritical Solution. She is a chemical engineer with a background in chemical and process system engineering. Titi has combined her work and studies with several volunteer tutoring and mentoring positions that have helped to underpin the development of science, chemistry, and mathematics skill in secondary school students. Welcome. And also, I would like to welcome Dr. Sella Kelici. She is an associate professor in material engineering and head for the London Centre for Energy Engineering at the School of the Engineering of London South Bank University. She is an expert of clean synthetic technology and materials engineering with a focus on producing high quality advanced functional materials with application in energy related areas and the environment. Among the awards she has received for her work are on the research project finalist in 2020 IKB Global Awards, Early Career Scientific Achievement Awards, first prize in the Material Innovation in 21st Century, and increased manufacturing values for her work on the synthesizers of graphene. Our next presenter, I would like to welcome Professor Nilesh Shah. He is a former head of Department of Chemical Engineering, Imperial College London, and a chemical engineer by training. He has co-authored over 300 technical papers on process system modeling and engineering with application to chemical, biochemical, and energy system, as well as the built environment and urban system. He is particularly interested in transfer of the technology from academia to industry. He provides consultancy services on process optimization, innovation, and industrial application of new technology to large number of the process industry and energy companies. I would like also to welcome Professor Stephen Dunn as the next panelist, who is Associate Dean of the Research Enterprise School of Engineering of London South Bank University and Professor of Material Engineering. He published over 140 articles in journals such as Advanced Material and Energy and Environment Science. His research interests include developing a fundamental understanding and developing ceramics to enhance chemical reaction with a focus on reducing the energy required to produce sustainable fuels and chemicals. He is currently working on processing of low carrier temperature ferroelectric materials, modifying the surface of ferroelectric materials with oxygen and hydrogen evolution catalysts, as well as novel way for carbon-sense nanostructure islands. His other research interests includes finding new application for functional material and the sustainable use of material for energy storage and generation. Our next, last but not least, renowned panelist, Jim Briggs, who is, I have been working with him more than 2 years to organizing this webinar and this built environment. He is an advisor with the Potence Natural Gas and LNG Consulting Group based in London. In the past 30 years, he has led numerous consulting assignments on LNG and natural gas projects, particularly concerning the development of natural gas resources. Formerly, he was the global manager of Potence Consulting Group. He is a highly experienced consultant in all aspects of oil and gas business. Previously, Jim was the head of the Nexans Global Petroleum and Chemical Consulting Division. Prior to formation of Nexan, he was a regional manager of Bechtel Consulting, covering Europe, Africa, and Middle East. Prior Bechtel, he managed biogas company and earlier was a staff member of the Commonwealth Secretary managing Industrial Aid Project. Jim is a Salon Fellow of the London Business School and graduate from Imperial College London, BSc in Chemical Engineering and Material Technology for Master of Science. He is a Chartered Engineer Fellow of Institute of Chemical Engineering. Welcome again to this webinar, and I would like to invite Professor Nilay Shah to share his slide and start his presentation on built environment and chemical engineering. Floor is yours, Prof. Nilay Shah.
Great, thanks very much. I hope you can see my screen.
Yes, we can see.
Okay, great. So welcome and thanks for the introduction. So I'll just do some scene setting. You know, why chemical engineering in the built environment? So I suppose most of you are now very familiar with this concept of urbanization. It really is one of the mega trends that is defining, you know, how societies will be and what the challenges for sustainability will be. And there's a couple of interesting things. So first of all, we often think about megacities when we think about urbanization. But actually, when you look at the picture that I show here, which shows the growth of the urban population and the stabilization of the rural population, most people actually live in small cities. And so coming up with solutions for small cities is really what we need, because actually big cities are like agglomerations of small cities. And the other really interesting thing that happens, particularly in the developing world, is as we urbanize, we also increase our standard of living and we increase our level of consumption. And so what we see in this picture is that the average Beijing dweller or average Bangkok dweller uses 3 times as much energy as the national average. So urbanization not only increases consumption of resources in cities because of population growth, but actually per capita there's also an increase. So the big battle against climate change is of course going to have to be faced everywhere, but cities is going to be one of the places we really do have to focus on. And of course people move into cities for economic reasons primarily, and what we see in this picture is what we would call an agglomeration index, which is, you know, how urbanized a country is. And you can see that if we correlate that against GDP, and these dots are different countries, you can see quite a strong correlation between degree of urbanization and economic development. And here we can see historical trends over time for different countries, where we're not plotting time, we're actually plotting how GDP has grown per capita, and something called a concentration index, where a value of 10 means everybody lives in a high density, relatively few settlements, and a concentration index of 0 means everybody's uniformly dispersed over the land mass. And you can see how countries have become more urbanized over time with a higher concentration index and increasing GDP per capita. So it's a trend that's not going to go away. Of course, we think of cities as iconic, and we think of their form and their architecture. But today we're really going to be talking about the engineering of cities. So if we look at cities as complex engineered systems, then they start to look quite similar, and we can think about the challenges as being quite common, and we can think about how engineering can help us to operate and design sustainable cities. So chemical engineering, we are very familiar with doing things like material and energy balances. And actually cities are complex systems, but they're systems through which resources flow and resources are converted. So in a way they're not that different from large complexes. And actually one of the reasons I got interested in working in city systems was thinking about how large petrochemical complexes had reduced their energy consumption per unit of production, had reduced their water consumption per unit of production, but we hadn't seen the same thing in cities. And yet I had a feeling that the sort of systems engineering thinking that went into large petrochemical complexes could probably be applied to cities. So what we see in this picture here is, you know, Neolithic people would consume 6 tons of material a year, whereas an average urban dweller will consume approximately 100 tons of material per year. And you can sort of track the material flow through a city, and that starts to give you an idea of how, for example, you could make that more sustainable, more circular. You could perhaps extract a lot of value from what are considered to be wastes. The other thing that, of course, we're all taught as chemical engineers is thermodynamics. And you can look at cities as thermodynamic systems. You can look at it in this picture in a sense of first law of thermodynamics, where we can look at primary energy input. This is a picture for Toronto. Toronto is probably not the most inefficient city, probably relatively efficient city. So we can see on the left the inputs of primary energy. On the right, we can see the final consumption of services, and you can see the flows and the conversions. And what we can see is a lot of waste. So cities, if you're lucky, from a first order perspective, use about 50% of the primary energy, so they're 50% efficient. If we use a second law effect and we look at exergy, cities are probably about 20% efficient. So there's a lot that can be done by thinking about city systems to make them more efficient. And so when we apply systems thinking, we also need some frameworks. And this is a framework that we've been using. We should think about cities as almost a connected hierarchy of 4 elements. At the bottom is how is the city actually organized? What is its location? What is its climate? What is the layout? What is the built environment made of? What opportunities are there to change the layout, to change the retrofit, to do any redesign? Because that already defines in many ways how effective it will be. Then the thing that maybe is a bit different from our normal engineered systems is, of course, cities have hundreds of thousands of millions of people in them, and they each behave and act in different ways. And the way in which they interact with this land use and built environment gives rise to various kinds of resource demands. And that allows us then to think about optimally serving those demands and optimizing the resource flow through the city. And then finally, we can think about operations and think about how do we manage those resource flows in real time, and how do we manage transport systems in real time. And just a couple of examples of what does this mean in practice. This is a new city design in China. It's an interesting location because it's quite cold in winter, it's quite hot in summer, it's coastal, and we were looking at a smart energy system design. And what we came up with is this interconnected 4-node, because there are four main nodes in this city, 1, 2, 3, and 4. We came up with a smart interconnected district heating and cooling system, which was really much more efficient and much lower carbon than the conventional ways of doing things like gas boilers and electric air conditioning. Another example of urban systems and chemical engineering is a place which has 2 challenges. It's in Southeast Asia. It is a place which experiences flooding and it experiences water scarcity. So what we were designing are some urban water collection systems which are supposed to do 2 things. They're supposed to reduce stress on the water infrastructure for stormwater and water treatment, but also to maximize harvesting of rainwater so that it can be reused for a number of non-drinking uses. And what we found was by doing some good systems engineering and some good process control, we could actually reduce freshwater consumption from the base configuration, where it's up here to somewhere down here, depending on the day. And instead of having periods of overflow, and that means essentially flooding in the urban environment, we could have no overflow just by redesigning not the tanks themselves, but the orifices and the control systems. So that's a whistle-stop tour of why I think chemical engineering has a big role to play in the urban environment, and I'm looking forward to the discussion later on.
Thank you, Nile, for a very interesting presentation and enlightening us in terms of how important is a chemical engineering role in a future and a smart cities That was very interesting presentation. I think I'll pass over to James for the sharing his slide for the next presentation. And later on, if there is any question, we'll ask from the panel. Thank you, James.
Okay, thank you very much for the introduction. I'm going to be talking, I hope everybody can see my slides. I'm going to be presenting some slides that have been prepared in consultation with one of my colleagues, Captain Doug Brown. But Doug lives in Houston, so I'm running the presentation to avoid him getting up at 2 o'clock in the morning, which we thought was a bit unreasonable. So I'm going to be talking about marine fuels and the issues around that, and touching on where chemical engineers fit into this. Marine fuels are not a big contributor to CO2. They're around 2% of global CO2 energy emissions. One of the issues, though, is that the emission reductions are not on track at the moment, according to the IEA's latest data. The target that's been set is a 40% reduction of CO2 by 2030 and a 70% by 2050, and that's against 2008 baselines. The sort of how and the driving force behind these this reduction is being driven by the International Maritime Organization, who've had a bit of success in their MARPOL implementation of low sulfur fuels, which came in 2020. That was actually surprisingly successful. So they're now trying to push into CO2 reduction. Their long-term aim is to achieve net zero, but only by about 2100. Their current initiatives are the Energy Efficiency Design Index, which came in 2013, which is designed to improve the efficiency of new ships. And then there's the existing ship initiative, which will be fully effective next year. The existing initiative is basically trying to grade ships from A to E, a bit like a domestic appliance. Grade D vessels are going to have 3 years to improve, and grade E 1 year. And the how this improvement is that this is going to be done in some cases by replacing engines or by some other clever modifications to the ships, and quite a few of the ships will be scrapped. But now to go further than that, to achieve the efficiency gain and to completely eliminate CO2, we need different fuels. At the moment, the industry is moving quite strongly into LNG as a fuel for ships, but that doesn't get us to net zero. The sort of options that we've got on the table at the moment to achieve net zero are things like ammonia, methanol, biofuels, hydrogen, batteries, nuclear, and sail assistance. The chemical engineers have a big role in all of these. The first two are definitely the front runners, ammonia and methanol, and they clearly have serious issues on safety, toxicity, and the ability to store them. But they do have the advantage that they can be used in fairly conventional diesel engines that run on ships. At least we think they can. Methanol engines have been run on. Ammonia is going to be done in the next 2 or 3 years, that some of the engine manufacturers are going to be doing some large-scale experiments on using ammonia as a fuel. Ammonia has essentially properties fairly close to LPGs, except for the fact that it's, of course, toxic and it doesn't emit any CO2 at all when it's burned. There is an industry initiative called Together in Safety that's looking at all these alternatives. At the moment, the interim conclusion was that the emphasis should be on methanol as the fuel for the future, either synthesized using renewable electricity or a bio source. At the moment, LNG is theoretically widely available. It's actually practically available in quite a few places. there's some use of bunker vessels that have been specially designed to refuel ships using LNG. There's quite a lot of truck-to-ship refueling for the smaller vessels, and it's fairly widely dispersed, but obviously a big concentration in Europe and in Asia, because those are the places where there's concern more about conventional pollution from marine fuels, which have traditionally been pretty dirty fuels. The bunker fuel business has always been where refineries get rid of things that they can't sell to anyone else. So those are the issues there. The ammonia and methanol, one of the reasons these are front runners is that looking at the map, there are lots of places where ammonia and methanol could be available. Obviously, nobody is doing this at the moment to bunker vessels, but it's fairly widely distributed around the world in places where these are manufactured or they're being used and imported. The big concern in the industry, particularly with ammonia, is safety in engine rooms. The industry were not very happy about the phase out of halon gases in engine room fire suppressants and the move over to CO2. It did that caused quite a few fatalities in the shipping industry. Engine rooms are very confined spaces and very noisy and very difficult places to work in. So introducing toxic materials in there is definitely not something that the industry is very keen on. But that is possibly the way we will have to go. Norway is quite interesting. They've gone heavily into battery and hybrid vessels. The largest battery vessel at the moment is nearly 140-meter long and operating in a fjord near Oslo as a passenger and vehicle ferry across the fjord. And DNV have identified that there's near 439 battery-powered vessels in service at the end of June, which is quite a few. I mean, it's still a drop in the ocean compared with the total number of vessels in the world, so close to 100,000. Europe accounts for 2/3 of the battery-powered vessels, and I suspect almost all of these are actually operating in Norway. Part of the driver for that is the Norwegians have got some legislation that's going to come in 2025, I believe, which pretty well prohibits emissions within the fields. So a lot of the vessels that are currently battery are actually hybrid. They're using the battery to get out of the field, and then they switch over to a diesel engine. And some of those are for the oil industry. Quite a few hybrid vessels now operating on the Norwegian sector of the North Sea. Batteries, though, themselves are not 100% safe. There's been at least 3 major incidents with battery failures. And interestingly, these are actually chemical engineering problems. They've been problems with keeping the battery cool. One, though, in the end was attributed to malfitting of a gasket in the cooling system that obstructed the flow. And then that was followed by the mistake of trying to set the fire out with salt water, which didn't go down terribly well on a lithium-ion battery. We are learning a lot from these incidents, but there's been some quite serious near misses in the industry with batteries. Where will we be in 2100? I think that's going to be down to the ingenuity of the engineers over the next 60 or 70 years to try and work out how we can achieve a net zero. It's probably not going to be one single magic solution. I suspect that it's going to be several different solutions, and some of which are going to be different according to the type of vessel, how far they travel, and the safety considerations, which probably can be managed easier on a larger vessel than a smaller one. We could also be eliminating some of the need for shipping, which would help us achieve net zero by distributing manufacturing better around the world, avoiding the amount of cross-trading of goods. There are vessels running on nuclear. The Russians have some icebreakers, and obviously there are nuclear submarines. So nuclear is a possible solution. The industry at the moment is still pretty nervous about it, but it may be a good solution for very large container vessels. So thank you. That's my very quick run through on one of the difficult to decarbonize sectors, the marine sector. Thank you very much.
Thank you, Jim, for a very informative presentation on net transportation. So just a very quick question, perhaps, James, I can ask you, and I would like to invite all panel to open the camera and we can start our discussion at this point. You mentioned early of your presentation, which under LNG, ammonia is going to be a future fuel, right? And I'm wondering, when we talk about zero net, and we talk about when ammonia is almost blaming of 42% of global warming. So how with this approach of having ammonia as a future fuel doesn't have impact, and how are we getting to the net zero target or not?
Well, the intention is not to leak the ammonia, I think, is the primary issue there. But it's really looking for what is a sensible fuel for running a diesel engine that doesn't emit CO2. And ammonia, when it burns, does not emit CO2. Now, with all fuels, there are slippage issues in engines. There are fugitive emissions from storage. So yes, that's always an issue. We don't seem to have a magic solution at the moment. But ammonia appeals to some because they know how to handle LPG. Ammonia is very similar to handle to LPG, and they think an engine will run happily on it.
Thank you, Jim, for the answer. Any other panels wants to give any comments on that question? So, all right. So in that case, I'll move on to our question. So our first question would be on how chemical engineers of the future contribute to addressing the major challenges for the livable future, modern, smart city and built environment, and what would be the next step? Maybe I will start with Nilesha.
Great, thanks. So I think the first thing is that chemical engineers won't be doing this on their own. I mean, I think the way we have to think about cities is as complex engineered systems with a strong social dimension. And when we think about future cities and making them livable, I think first of all you have to set some overall targets which can be based on, you know, how cities are doing today in terms of material consumption, energy consumption, direct emissions, but also very importantly indirect emissions, water use and waste. And you have to set, you know, really ambitious targets for what you want those to be, because I find that engineers collectively, they're most creative when they're given a challenging problem. And then you start to think about existing cities and new cities, and you think about how can you collaboratively design new ways of moving around, new ways of living, new ways of working, new ways of producing things, and new ways of managing those engineered systems of transport, energy, waste, and water to hit those targets. So each of those have a strong chemical engineering component. So we've got, you know, fuels and energy storage for transport. We've got, you know, fresh water and wastewater management. We've got solid waste management. We've got a lot of things to contribute in distributed energy systems and integrated energy systems. But I think that the two things that come through are, first of all, have to collaborate with mechanical, electrical, civil engineers, but also social scientists, economists, and so on. And second of all, I think the one thing that chemical engineers are really good at is systems thinking. You know, we're very good at thinking about how different elements of a system, whether that's a process flow sheet or a device or a wider system like a complex, how those elements contribute to the performance of the system as a whole. So I think that's a particular aspect of chemical engineering that is a bit different from other engineering disciplines. So I think it, as I say, it starts by setting ambitious targets and then working collaboratively with other disciplines to come up with creative ways of meeting those.
Thank you, Nile. Maybe Titi, do you have any point on this question?
Yes, I think it's basically similar to what Nile has said, but what I would touch on is in terms of thinking about the future as well. So a lot of, you know, it's understanding how we can also present these challenges in a way that is understandable to even the next generation as well. And that's getting them interested in engineering and getting them interested in how engineering, not just engineering as a profession, but the sort of contributions that we make as engineers to be able to solve these problems collaboratively. And just, you know, also thinking about, just to touch on the point on systems thinking as well, when we're thinking about the safety of any solutions that we're bringing about for these challenges, we need to collaborate. So whilst, yes, as chemical engineers, we have this very unique set of skills, we also need to collaborate with specialists in other parts of engineering as well to be able to, you know, bring about a solution that works for everyone, that is safe for everyone, that, you know, is also sustainable in the long term as well.
Yeah, thank you, Titi. Maybe Steve, do you want to add anything on that?
Hopefully unmuted. Yeah, I thought that was really fascinating, especially what Nelia was saying about the amount of waste in the system. And one of the things I think that is going to be important going forward is trying to find some way of capturing that waste and doing something with it. So waste heat or waste water, and using low energy solutions to recycle that and therefore, you know, move that system closer to a net zero. So I think the diagrams we saw with the ships and also the cities, the nodes and stuff, obviously fascinating and a really nice sort of tie into sort of, you know, textbook chemical engineering, if you like, to then move it into the real world. I think, yeah, anything that we can do to close that loop and put more on the back end would be absolutely fascinating. Certainly for ships, improving their efficiency, not just in terms of engines, but their efficiency through the water as well, if possible. And also the cities, just capturing some of the waste that comes out the back end and then pumping that back through again into the front of the system, sort of thermoelectric type materials or energy harvesting, energy scavenging type systems enable us to do that. So I think there's lots of opportunities, and it's great to hear that we're not just talking about chemical engineering. I think, you know, the mechanical engineers, the civil engineers, everyone involved in urban environment and pushing that out even into, you know, small villages and cities. So it's off grid. A lot of was fascinated a few years ago when people were putting tiny little PVs to battery storage in little villages in India and Southeast Asia, and the differences that had for quality of life and quality of education, and the way that more of the population could engage in education and improving their societal gains was great. So I think it's a really interesting topic, and certainly I hadn't really been aware, although I've sat in the room with Neil a few times, I hadn't been aware of what he was doing around this urbanization. So I think, yeah, really lots of opportunities and fascinating stuff to be involved in.
That's great to know that. And maybe I ask Claire to put her remark on that question.
Yeah, so from my perspective, I think it's, you know, with a focus on transport in urbanized areas, thinking about the right technology to move people around those urban environments, and how, from an energy perspective, we look at how we're storing and using and so transferring energy. And I think that, yeah, I also kind of echo what Steve said about Nile's comments. It's really fascinating, that systems level thinking about how we bring together transport and energy, particularly in those urbanized environments where often people have a lot of different options, helping them to pick the right option, understanding where the impacts are going to be with the different propulsion units and the ways that we can make and store energy now in different ways is going to be super important.
That's great. Yeah, I agree with you. The energy is now issues. Perhaps, Suella, do you want to add more on the points that was Rose?
I mean, what is, yes, thank you. What is coming across here is just the only key message is efficiency, and more importantly, you know, energy efficiency is really, really, really important, and is whatever in urbanization of our cities or our you know, civilization, etc. It is important for to have a marriage of disciplines. Chemical engineers, they can't exist alone. Same as mechanical engineers, same as materials engineers or everyone else. It is a marriage of disciplines to bring sustainable solution and to bring efficient urban centers. So in other words, we need to have you know, optimal resources and also less emission, which is the main goal. And as an engineer, not only for, you know, the energy efficiency, but also the water treatment or the wastewater or the recycling of the water, it is one of the key messages as a chemical engineer we have to take away. And for this, it is important, and echoing the same messages that panelists have already said, we need to also have knowledge transfer. Not only that, but we need to kind of get involved the future generation. We need to educate the public. We've seen quite recently in UK and also some of the issues, actually, they've been influenced by geopolitical areas. We've seen, like, we kind of, you know, we have a ban on water, using the water, or, you know, the energies, etc. So how do we make it more efficient? How do we educate the public in order to have, or to make optimum use of our resources?
Amazing points.
Thank
I
you.
agree with you, because again, in the Nile presentation, when he was talking about the layer of the behavior, I think this is where maybe we engineer forget about it, that behavioral, it's very important to, you know, get the community, understand, train them, and as you said, the future talent will be well aware about what the net zero is exactly. So Jim, perhaps you want to add something on this point, please.
Well, I think always the challenging part of the system is the human being. Getting them to do whatever it is that you want them to do is not easy. You've got to create a situation where it's what they want to do, basically. I think, but it's possible. It's somewhere where we need to work more with people who are more skilled at human motivation than perhaps we are, because I think the danger sometimes with engineers is we become too mechanistic about getting things done, and we say this is the obvious thing that everybody should be doing, and they then don't do it. I sometimes observe my wife, who's a special needs teacher of very young children at work, and the way she gets people to do things is by a lot of subtle positive feedback. But maybe it's something that we ought to consider in chemical engineering education, that we need a bit more emphasis on recognizing that people are involved and how we motivate people to do the right thing.
That's, yeah, I really like the points, because that's where we think about conventional chemical engineering, things about oil and gas only. So now we are coming towards the human behavior, and now we know what the urbanization, population growth, and now we call it climate change. All this needs to have a resilient cities. As all of you in a sense mentioned, this needs an integrated decision making or multidisciplinary approach. Now I'm thinking how far, I mean, all of us in a sense agreed the multidisciplinary is very important, involving other discipline, architecture, material technologies, civil engineers, historian, perhaps even lawyer. They need to be involved with this topic. But how far is a chemical engineer, and how the knowledge and experience and ideas of the chemical engineer can be brought into the working environment already is a realm of other established disciplines. So I really want to know how we can go with this. Perhaps we start from Steve. Yes, I know.
Sorry, I'm a Teams person, and I'm trying to find
no,
all the buttons. It's like
no,
another software package. Sorry, I was actually sorry. I wasn't quite listening. I was listening. I was reading some of the chat as you were reading out your question there, especially the role of the green hydrogen in the marine sector. So and I was kind of thinking about that. So could you just like repeat your question very quickly, Nazrin? Sorry.
Okay. Don't worry. I'm just thinking, because we're addressing all this matter of the multidisciplinary, and you guys mentioned having a different discipline. Now, how we go for this, because how the knowledge, experience, and idea of chemical engineers can be brought up to the working environment.
Yeah, I think I think we've all touched on it, that this multidisciplinary approach is really, really important. And I think over, what I've observed, I've been in academia for a bit. I had a role in industry for a little bit and back into academia. And I think what I've observed is that working independently as a pillar of one, you think a chemical engineer, a mechanical engineer, a chemist, a physicist, or it's becoming increasingly difficult and more challenging as time goes on. The lines are naturally becoming more and more blurred as people start to move across disciplines and see benefits from other disciplines. Certainly, when you're talking about a large conurbation or a large group of people, then they don't see chemical engineers, mechanical engineers, physicists or chemists or process scientists or whatever. They just see an output or a change to their quality of life. And I think it's important that we focus on the end game and not what we're trying to do as individuals. But the purpose is to produce a better urban environment that uses less resources to enable the world to have an equal quality of life, so that we don't have such a disparity between Europe and the West and the rest of the world. So I think for me personally, you can find hundreds of anecdotes of where working together across disciplines has made a massive difference. And if people do try and isolate themselves, I think they will increasingly find themselves literally isolated and not talking to the right people. So yeah, I guess I'm waffling a little bit. I just think for me, it's been my career. I've had people from electrical engineers to physicists to chemical engineers to chemists working in my research group, and I've seen our graduates from chemical engineering programs go into what you would consider to be a mechanical engineering work stream. So I do think it's really important and something that we should be supporting as much as possible.
Thank you. So what do you think, Claire, about that? How we go for this?
Yeah, I'd take that thought like a step further, actually, and think about where those young engineers or scientists of any discipline are being given experience. So I think it's actually more of a call to more experienced and distinguished colleagues who are listening into this today to say, how can we give those young people opportunities, or those that are new to the industry but maybe have come from outside. There's a lot of development going on in all these areas. We've heard about shipping and different fuels and different propulsion units, as well as different ways of organizing the built environment. There's so much opportunity, but I think sometimes it must be quite daunting to know where to start. So I think my reflection would be, it's great to work collaboratively and across disciplines, but think about how we can give opening doors for others that are in the industry. It might be as much or as little as a couple of days shadowing to a long-term placement, or taking a chance on someone who doesn't look or feel like a traditional kind of whatever person in your field might be. I think that's the only way we're going to increase help people get into the industry and to come and bring a diversity to all of these disciplines. And that's something I kind of actively try to do, because you don't know what those people are going to bring from other parts of their experience. I think, you know, Steve made a point there about his experiences of being academia and industry, and I guess that's probably my final point, which is that sometimes academia and industry can feel like two kind of completely different worlds, but actually it's so important to bring them together as closely as possible. I think we're seeing really interesting, hugely valuable results from the Faraday Battery Institute and the Faraday Battery Challenge, looking specifically at the battery industry in the UK. So yeah, I'm kind of interested to learn from fellow panelists as well if there are other kind of cross sector, cross industry kind of activities going on in other areas as we, you know, push to decarbonize.
Yeah, thank you, Claire, for the points. And maybe Titi, do you want to add something on?
Yeah, absolutely. I mean, just to continue on with, I guess, Claire's train of thought as well, is as a chemical engineer, I've worked as a safety engineer in the rail industry as well. And whilst it did feel like a very non-chemical engineering industry, I find that I was able to sort of bring about that, you know, diversity of thought as well into the team. And you know, it goes back to what I think really also showed on his slides, where he talked about, you know, as chemical engineers, we understand the principle of mass balance and thermodynamics, but then using it not just for, okay, you know, this is the process going from A to B, but thinking about it in the context of cities or systems as well. So I think that if, you know, it is a multidisciplinary approach that we need to work with each other, or with one another rather, but also we need to, even as chemical engineers, we can take the foundations of what we've learned and sort of apply it differently. And just going back to what Steve mentioned as well, that focusing on the aim of, you know, we are trying to solve a challenge. So even if it's not necessarily, you know, producing a chemical or, you know, that sort of thing, you know, as long as you're able to use what you understand or what you know to be able to move to get from the challenge to the solution, then I think that, you know, as chemical engineers, we will be contributing our quota to solving these challenges.
Yeah, I agree with you, and it's very important to rethink and redesign and looking at also circular economy. So Ella, would you like to add your remark on this matter?
Yes, I mean, it is also about the transferable skills, and it's also adapting the skills of chemical engineering, as we have our motto in chemical engineering in LSVU, is trying to solve the needs of today and future needs as well. So as a chemical engineer, we have to be flexible. We have to adapt our skills in order to kind of provide solution to global challenges, and as the one we're talking about today, urbanization and transport and energy efficiency and water efficiency.
Yeah, thank you. That's good. And James, perhaps you want to add? Yeah,
well, I'm happy to add, particularly on the issue of different inputs. I've been running consultancy businesses all my career, and I would never recruit people in the same image as myself. I recruited economists, I recruited other forms of engineers, I recruited geologists. I've just got some friends coming to the house who worked with me for a very long time soon, and one's a geologist, one's an economist, one's an electrical engineer, one's another electrical engineer from the power sector, and one's an environmentalist. And they're sort of typical of the need you have to have when you're trying to solve problems. You need a wide range of different skills. Now, of course, saying that, chemical engineers usually were amongst the best trained and most general in solving different problems of the team, of the people I recruited. So, and the other thing I used to recruit is try to recruit people from around the world, wherever I could, because it's just good for business. Brings in lots of new ideas, and as I think Steve said, you know, a lot of technical advances are made by applying an idea from one industry to a completely different situation, and suddenly you find you've got a big technical advance. But yeah, but that's been my philosophy through my career, is to do that.
Yeah.
You know, even back in Bechtel days, we worked in very multidisciplinary teams when we were doing the industrial city plannings for places in Saudi and the UAE. Yep.
Yeah, that's good. And then perhaps back to Nile, because I know you are as one of the very unique chemical engineer who is really working on the built environment and looking at this issues of the being multidisciplinary and talking about net zero emission. And we're talking about, okay, the buildings in whole world maybe are the culprit of 40% to the emission contribution. So what's your point of view on that?
For me, I always like to start from what the challenge actually is, rather than what is the, you know, the discipline or the technical solution. Because I think if you set yourself some interesting challenges and you don't sort of specify the solution, you specify the outcome that you want. So you talk about the outcome. So you want, for example, you know, quite different performance measures in terms of resource consumption and energy and so on, but also outcomes in terms of people's quality of life. So you set these aspirations which are quite different, and then you can convene almost any group of intelligent people, almost independent of their technical training sometimes, and you can actually come up with some quite different things, because often I think we just get stuck in our way of thinking because that's how we are familiar with things. So I think that's where, you know, people like urban planners and architects are really good to have it in part of that conversation, because they're quite creative, but they don't necessarily know the technical possibilities. So they don't know the different ways in which you can supply transport energy, how you can heat and cool buildings, how you can treat water, and so on. So that's where, of course, the disciplines do come into their own. So I think it's this high-level challenges and high-level outcomes is what you use to drive the creativity.
Yeah, thanks for that. And all right, so moving forward, current major of the transportation forms needs chemical engineer to ensure they are designed safely, right? And the economic growth by 20th century is driven by the reduction in the cost and increase in the speed of the transportation and goods. So now we want to know chemical engineer produce fuel to make this possible to refining and furthering the processing of the crude oil. A question here is, transport is often highlighted as the most challenging sector to decarbonize. Oil-based fuel have given us over a century of low-cost, convenient travel from fuel that have high energy density and manageable hazards. How do you see chemical engineering or engineers responding to the challenge of the replacing these with zero carbon alternative, which are currently inferior to cost, energy, and density and hazards? Perhaps maybe Claire, do you want to start?
Thank you. Yeah, so in my work, you know, I focus on electric vehicles, predominantly passenger, some smaller vans, but actually transport is an enormous topic, and you know, goes all the way to what Jim was talking about in terms of shipping, maritime applications, to aviation, and aviation itself in terms of passenger transport and transporting goods using drones and other light aircraft. So it's an enormous challenge in terms of transport. But there were two things you mentioned there in the introduction that I would pick up on. One is energy density and one is manageable hazard. I think in terms of, you know, the way that we have relied on fossil fuels and the way that fossil fuels have been used and applied, and the way that whole application of that technology has developed over 100 or plus years, we're in a really interesting point in the transition to alternative propulsion technologies, where the new technologies are being compared directly with those matured technologies. And I think so that in terms of energy density, you know, we're seeing an explosion in innovation across every part of the supply chain. I mean, just taking lithium-ion batteries as an example, we're seeing renewed interest in mining and mining technologies around the UK. In fact, there's a really interesting and exciting industry growing up around regenerating mining in existing areas in Cornwall, for example. New technologies and very much a chemical engineering challenge here around extracting battery grade lithium from geothermal waters in Cornwall with a co-located thermal generated steam power plant. There's a really interesting opportunities in the battery supply chain. But then if we talk about, say, bringing it back to energy density, lithium ion is a really interesting one where the energy density is increasing year on year. And so those challenges, I think, are being met. I think where the next wave of innovation is coming is in alternative battery chemistries and battery technologies. And that's replicated across all these different potential propulsion fuels and technologies. And again, Jim really enjoyed your talk about the different ways of propelling much larger vessels. And then in terms of manageable hazards, again, we've come such a long way in understanding how to handle materials and handling them as part of a system. Actually, I think we're making even more rapid progress in terms of decarbonising transport in safer and cleaner ways. And then the final piece, I'll bring it back, is not to forget where the energy is going to come from for not just as the primary fuel, because with all of these fuels we talk about green hydrogen, ammonia and others, we still need to use energy to produce those fuels, but also the energy that's embodied in all of these supply chains and all of these systems. I think sometimes we can hone in closely on electric vehicles of the future or scooters or eVTOL, these human carrying drones. Actually, you've got to think much more broadly as well, the whole system, and think about where does the energy come from for all of the manufacturing of these vehicles, for the recycling of these vehicles, and also for the production of that energy. So thinking about renewable energy and storing of energy and using energy at times when it's greenest is going to be really important. And perhaps that's not something that we have thought about as part of that whole system thinking before in transport. So yeah, lots of interesting challenges to work on there in terms of the vehicles themselves, the propulsion technologies, and the energy that gets embodied in the whole supply chain and life of those vehicles.
Yeah, that's great. Yeah, to understand this. Maybe Nile, do you want to add anything on that?
Yeah, I think what we have to face is the fact that the future transport energy system is going to be much more heterogeneous, and I think that's an answer a lot of people don't like, because we've got used to this single solution, one size fits all of fossil fuels. Of course, we refine them into four main categories of marine fuels, diesel, jet fuel, and gasoline. And the future is just going to be more heterogeneous, and we're going to have to find how to optimize those different niches. So if you've got your personal light goods vehicles, your small light duty vehicles, your heavy goods vehicles, rail, close coastal shipping, long distance shipping, short aviation, long aviation, we're going to see different solutions in those, and those are going to evolve over time. There'll be more hybridization. One area I found incredibly promising, one of the things I've been involved in, I'm a co-founder of a synthetic fuel business, which is actually making synthetic hydrocarbons from CO2 from the atmosphere and hydrogen. And I was really pleasantly surprised at how well you can actually tailor the catalysis and the reaction engineering to make fuels that are actually equivalent in performance to our known hydrocarbons, but they're actually a lot better, because you're synthesizing from scratch. You can get rid of things you don't want, like naphthalenes. There's no sulfur, there's no nitrogen. You can tune the aromatics content and so on. So I think there's going to be a lot of interesting future in synthesizing a range of fuels, from simple molecules like methanol, ammonia, to complex hydrocarbons like jet fuel or different kinds of maritime fuel. I saw a really interesting creative approach the other day for maritime fuel, which was using methanol as an organosolve extractant to extract lignin from biomass. And then instead of trying to do anything with that, you take that solvent and the extracted lignin, and it's a marine fuel in its own right. So you know, one of the problems with trying to do things with lignin is you have to extract it from wood, and then you have to recover it from the solvent, and that's very energy intensive because you've got to, you know, somehow distill off the solvent or whatever you do. So this idea to make a marine fuel, which is essentially a mix of lignin, which has been partially deconstructed into smaller oligomers, and methanol, it apparently works very well in a typical marine engine. So I think there'll be a lot of creative solutions like this. So we'll have to see how these different solutions coexist with each other. And of course, as Claire said, we're going to need quite a lot of more primary energy because we are currently relying on this endowed reserve of fossil fuels. I mean, you know, the amounts of exajoules we extract every year in terms of natural gas and oil will have to be replaced by energy we generate primarily electrically or to some extent harvest through biomass. So we're going to have, you know, far greater primary energy generation because we're not extracting energy, and I think that's the bit that people are missing as well. So we need more energy in generation anyway because we're going to be replacing fossil fuels directly, primarily with electricity, heating and transport. But then that electricity is also going to go into these new chemistries, which are driven primarily by the energy content and reducing power of hydrogen. So we will need a lot more, you know, renewable energy, nuclear energy, and, you know, some degree of biomass. But I'm, you know, I'm not sure, you know, how much biomass we can reliably expect to see for this purpose.
That's interesting. And perhaps we hear from Steve. Would you like to add on this?
Yeah, thanks. So I think some really interesting points coming through. So from my perspective, I think the comments about we're obviously going to have to replace what we dig out of the ground with alternative energy sources. Otherwise, we're just going to keep getting hotter and hotter and hotter. And I think the evidence of human intervention into climate change is becoming obvious this summer in London, if not around the world. I think one of the things that's often forgotten is we need a change in behaviours. The average car sits motionless for 97 or 95% of its time. This is not a good use of a £20,000 asset that has taken a lot of CO2. So I think we need a change in behaviours. And Nile saying, you know, heterogeneous, I think we're moving to almost like a zip car type thing where we have in urban areas, certainly you have a pool of vehicles that perhaps people can dip in and dip out of rather than personal ownership. Without that kind of behaviour in developed nations, I think we're really going to struggle. There was a report recently, I think WMG did, that effectively said there isn't the global capacity to make battery powered vehicles at the rate that we make internal combustion engine vehicles, and it's not predicted to get there for a very long time. So we'll be chasing our tails. So I do think that you know, converting what we have in the atmosphere around us into something useful is really important, be that an ethanol or a methanol or a longer hydrocarbon that has a slightly higher energy density, going back to the original question. And I think also that we can get away with lower energy density fuels if we change our behaviours and we change the way that we travel, and we start to think a little bit more holistically about the impact that our individual behaviours have. In the West, I mean, certainly if you go to other parts of the world, a 40-kilometre commute to and from work in a car is not a standard behaviour. It's not something people do in many parts of the world. It's a Western privilege in many ways, and I think we need to think about that. But then for globalization and getting goods around the world and feeding us and clothing us, we need to be thinking very carefully about the way that the goods are transported globally. So Jim's sort of experience in the global shipping industry is going to become a really vital way of moving stuff around the world to enable us to produce things cost effectively. And I think when I say cost effective, I mean energy as well as dollar effectively. So there are parts of the world where it's more energy efficient to do something than it is in other parts of the world. So for example, Iceland's got a lot of geothermal, so you can get a lot of high energy processing in Iceland for virtually net zero, because they can use low energy solutions. So, and other parts of the world have got benefits of different energy solutions. So I think, yeah, I mean, I agree with everything so far. We need to use the natural resources that we have and the renewable resources more efficiently and more effectively. And we need to think a little bit about the way that we expect to travel. And I think those changes will happen naturally over the next few years, especially if the price of energy stays as it is, with some of the scary numbers that you're reading in the news recently about £4,000 a year to heat and cool your house. Is something that will naturally change people's behaviours, and hopefully not with too much penalty for them, because it's going to be a group of society that are going to suffer. So yeah, I think we're right. We just need to be holistic. Heterogeneous, I think, is a great word to sum it up, and move forward in that way.
Yeah, that's great. Sola, do you want to add any more on this matter? Because I believe material engineering.
Very briefly on yes, very briefly on this, multi, options that we have to produce fuel. All will come down to, life cycle analysis, and above all, in terms of the cost and efficiency. And as Jim also mentioned, it is very important, and one of the roles of chemical engineers is on terms of the safety and operational risk management for all the fuels. Because if we're talking about the hydrogen or using green hydrogen as a fuel, what are the options for storage, and how do we deal with flammability in large-scale production, or how do we deal with ignition of hydrogen? Or if we talk about, the biofuels, what are the NOx standards associated with it, or the emission associated, and how do we handle ammonia? So all these issues, when we're talking about large-scale production, when we talk about from, moving from pilot scale or from ideas to kind of implementation of those technologies, yes, there are huge commercial and technical limitations. But I also want to kind of re-emphasize on the point that Claire was making in terms of, yes, we will have this electrical vehicles and cars, etc. But where is the whole energy is coming in, and will we be able, for instance, if every household would have an electrical car, can we charge at the same time, or how are we going to have a charging point in every household? So that comes down also to, or links well with smart cities and urbanization, and those things, they need to be thought well in advance in order to kind of reach the target goals for urbanization and transport for smart cities.
Thank you, Sola. Maybe welcome. Titi, do you want to add anything on this matter?
Yeah, no, very interesting points have been raised. I just wanted to add a piece as well on the fact that there's that point, I think we mentioned it while talking on the previous topic, in terms of educating the public. So basically giving the public the understanding that, there's a shift in terms of how energy, or, what the way we are going to, fuel our heat, fuel our heating, our electricity, our transport, and all of that. So basically, we need to be educating in, I guess, as simple language as possible, for people to understand a bit better, and that would then, cause the change in behaviors that, Steve has mentioned before as well. So I think that that's really important, that, we have that alongside the sort of the innovations that we're having. I agree, there's so many, ways of thinking now, that, there's so many innovative ways of doing things now. I think I saw recently about hydrogen being stored in boron hydride, sort of as a way of, as opposed to liquid hydrogen, and maybe that would solve some of the challenges that, are some of the challenges of the safety hazards associated with liquid hydrogen storage as well. And just on the safety aspect, I think that whilst, innovations are moving at a very high pace as well, fast pace rather, I think there's also a point about, learning from our previous mistakes, so not forgetting, or learning from previous accidents, and making sure that that learning is being incorporated into the technologies that we're building going forward.
Thank you, Titi. And we do have a lot of questions in chat box, but then Jim, would you like to add something on this matter? Then we can move on to the chat box.
Well, I do think we've been skirting around it a little bit, but one of the biggest drivers for human behaviour is money. And in the end, I think we have got to be make sure that the drivers are correct to drive behaviour the way we want it. So I'm personally in favour of things like carbon taxes and with border pricing to compensate. I think that is a useful way. I think we are in a weird situation, certainly in Europe at the moment, with energy prices. It's not a real long-term situation. This is an artifact of the fact that my industry cannot react on a timescale less than 5 or 6 years to major structural changes. So if you take out Russian gas supplies out of Europe, it will throw the world natural gas industry sideways for at least 5 or 6 years before we can rebalance. But current prices are not long-term. Current prices in Europe are not true long-term prices that you can really make long-term decisions about, which is an issue at the moment. I also find when I talk to ordinary people that they're not terrible. Everybody is concerned about climate change, but they don't want to pay. And I think there needs to be a lot more honesty from politicians and from ourselves that this is going to be expensive to achieve net zero. This is not going to be cheap. And I think some of the publicity that we get as technologists proclaiming the latest clever idea that's going to save the world, and we're doing this with all good intent, I'm sure, to get funding and everything, but it keeps reinforcing the view in the public's mind that there's going to be a magic solution to climate change and that they don't need to worry that it's going to impact their standard of living.
Thank you so much, Jim. We are running out of the time, and I have plenty of questions, very good question in the chat box. Just I'm bringing one question to the panelists, which is coming from the John Pritchard, ChemEng Chief Executive. He's asking, he's mentioning, when I took over ChemEng Chief Executive with the background as a civil engineer, I had a little appreciation as to how chemical engineers could contribute to my discipline. However, as my understanding of chemical engineering developed, it became increasingly clear that we were missing an opportunity. I believe that we need to embed multidisciplinary project at the undergraduate stage. Does the panel see degree accreditation as a lever that can help or hinder this? Who wants to answer? Maybe Nilay? You want to start?
Yeah, sure. I think what we need to do is to take advantage of the flexibility in the curricula, because when you look at most of the accredited engineering programs, not just chemical, but all the others, they have this idea of extending modules, so modules that build on your fundamental understanding of your discipline, but allow you to explore it in different contexts and extending contexts. So I think that's where, as educators, we should be exposing our students to how those core concepts, so in our case, thermodynamics, material balances, energy balances, process design, can actually be applied in contexts different from the ones that they may have learned in the early part of their degree. So although all the professional engineering institutions have certain criteria and learning outcomes, they generally also have this concept of, you can spend quite a good proportion of your credits on these extending modules, which although still are about engineering competence, they can be very broad. So I think that's where we should look to first, because I think we don't need to rewrite any of our any of the accreditation outcomes, because they already talk a lot about ethics, about sustainability, the role of engineers in society, and so on. So I think it's the context within which we teach that. And I think teaching things about national systems, global systems, urban systems, and the role of engineers is the kind of thing we can do in a lot of curricula.
Thank you, Nile. And maybe Suella, from your point of view, what do you think about that question?
Well, yes, I do agree, and it goes back to the previous point that it's not only those core fundamentals. We need to adapt those core fundamentals of chemical engineering to solve global challenges, and that is through, as Neil mentioned, incorporation on kind of thermodynamics, etc., into other areas. But also we have research projects as well, which actually the student can adapt and learn and make a contribution or learn a new topic on how chemical engineering skills can be adapted to a variety of other areas in order to solve global challenges.
Yeah, thank you, Suella. And I would like to hear from Steve from academia. What's your perspective on this?
So I think I agree pretty much with what Nile was saying there. I mean, we the final sort of year design projects and group projects are actually quite broad curriculum based. They're not just chemical engineering. They're chemical engineering in the context of sort of some global or local or other challenge, which gives the students an opportunity to look at how their previous kind of textbook or first year textbook, then moving into something more experiential learning, can actually dovetail into some of the bigger challenges. So I actually think I'm a chemist, material scientist, engineer by meandering through a whole bunch of different sort of career choices and career options. I actually think chemical engineering, and we were validated not that long ago, that the whole process does highlight that chemical engineers need to fit with other engineers, because the chemical engineering discipline is unique, but it's also very, very much dovetailed into the other core engineering disciplines. So I think we already do that in many ways. I don't see there's a real drive to change what we need to do at validation in order to generate engineers that have a real value in the workplace. And I think the fact that our engineers do a year in industry, come back, finish off their degree, then end up working in all sorts of different sectors, and decreasingly oil and gas, and now more in water and pharma and various other sectors, indicates that actually we do a pretty good job at producing engineers that tick. And I'm kind of going back to Jim's comment when he said his chemical engineers he recruited in the past were the ones he found kind of creative and vibrant and really working in the team. And I think that speaks to the design projects and the projects that we do in the undergraduate programs that lead to our final graduates.
Thank you, Steve, for a very great point. Perhaps, Claire, what's your point of view from the industrial part in this question?
Yeah, my reflection from industry is actually there's a huge amount going on which people can take advantage of, which you might consider to be educational, not just for those in academic institutions who are studying for a first degree, but continuing throughout our careers, and actually seeking out opportunities to learn is going to be it's always an important skill, but it's increasingly important given this cross-disciplinary ways of working that we've been talking about. So I guess a good example of that would be the Energy Institute, which puts on a wide variety of different activities for young professionals, for example, really busy, vibrant branches in different cities, tying up with different universities and academic institutions, but also with young professionals who are out there working in different ways and different places. And these are all kind of free activities or very low cost. I think also what we've all been through in the last couple of years in terms of this, the huge shift in ways of working, accessing information and accessing each other. I would kind of highlight that as well to young engineers coming through, thinking about using the internet, using LinkedIn to reach out to people, to go out there and kind of grasp opportunities to network and reach people that you might not be able to get to, within that kind of physical location of your one institution that you're studying in right now. And I think then more broadly, you know, there's lots and lots of opportunity out there to join things like this, like today, to learn and network and to gain information which you may not gain on your on your course in your particular engineering discipline. So there's a huge amount of information out there to be had, an awful lot of it for free, and also to network in ways which maybe we weren't doing even just a couple of years ago. So lots of opportunity out there outside of your traditional, I guess, studying route.
Thank you, Claire. So yes, Jim, would you like to add something?
Yeah, I just on the question of broadening the curriculum. I mean, I spent quite a few number of years recruiting from around the world and recruiting from off different courses. I do say that the UK chemical engineers I recruited were work ready more than pretty well anywhere else I recruited from. And I think part of some of the concern about broadening the curriculum too much is particularly one North American country. A lot of the universities allow a very mix and match approach to what you study on an engineering degree, and some of the modules they end up doing didn't strike me as being terribly useful or terribly helpful in their development. And so I would just caution about going too far with this. Oh, let's really broaden the curriculum, but let's not get too far into media studies and things like that. It doesn't make them terribly good work-ready individuals. So
Yeah,
that was just a caution there as to how far we go. But I do think doing economics, doing how you motivate people, incredibly important.
Thank you, Jim. I think we are approaching to the time finishing, but Titi, perhaps you have a closing mark to add on this question and curriculum review.
Yeah, I think my take on it is what university or what your degree does for you is to teach you how to learn. So you learn how to learn when you get in there. And then wherever you find yourself, whether it's continuing in academia or working in industry, then you basically start to learn, you use those skills. So the fact that you've learned, so apart from learning the technical bits of it, you also learn how to then apply it and how to learn other things as well. Because I mean, if it was based solely on what we learned in school, then we would have to, keep going especially at the rate at which, innovation and new concepts are coming up. We'd have to keep, going to sort of top of our university degree or whatever degree that we have. So I think that it's so having that mindset in terms of, okay, I've learned something, I understand the basic concepts, and then just really honing in on, I guess, your analytical skills, your understanding of how to learn something or hear someone from a different discipline of engineering say something, and then get the right amount of information, knowing what questions to ask that can then strengthen your understanding as well. I think is really important. And I would say, like, maybe for young professionals like myself, volunteering is also a really good way to sort of improve or learn things outside of your industry, so get to know other things about your industry, because with that you're able to understand a little bit about other industries, probably in engineering, but maybe even outside of that as well, and that gives you opportunities to transfer those skills or transfer that knowledge into what you're doing. So those are two things I would say, outside of university can help.
Yeah, thank you, Titi. I agree with all the points because that's very important. At the same time, but with new education system, which we talking about the Buffett course, I don't know, and the different courses. So a little bit we are moving forward towards a new system of education. And I think this is where, apart from focusing on chemical engineer, how chemical engineer can changes the social behavior, in home and in business, in industry, And I think earlier Sola mentioned mentioned of the future talents will be well educated towards to understand the whole system and how to energy saving works, even maybe it's starting from kindergarten. There are many important and interesting questions in the chat box, but unfortunately, since we are running out of the time, just a little bit looking at the closing mark of the summarizing. It was very interesting to understand the chemical engineering and challenges through the urbanization and built environment and transport sectors, and how the and what engineer skill can require for the future chemical engineers, even the curriculum review itself by the new method of the education we do have, and the perspective of chemical engineer for the future livable and resilient city. The reflection of this webinar is going to be in a website. Later, maybe you can look at the website reflection. And also, I would like to invite all audience to register for the next month seminar on the 14 December. 14 September 2020 for the health. You can check the website. And with that, I'm going to conclude this session. And I would like to thank all the panelists for the very interesting points and giving us time at this time of August. Everybody is on a holiday, on leave. So it was great and amazing to have all of you here, and hope see you all of you next month again. Have a good day and cheers. Bye.